Okay, so this time we're going to take a look at electromagnetism, magnetism itself in particular, but the interactions between magnetic fields and charged particles, among other things. So this is something new when it comes to magnetism for a lot of people. It's unfrozen. Okay, good. But we're going to hopefully demystify some of that. So the first one that we're going to take a look at, what we'll look at in this problem, is the Lorentz force. Lorentz force is usually F sub B, and that's the force on a charged particle moving through a magnetic field. Now technically the full Lorentz force actually includes an electric field in there, so you could account for both electric and magnetic fields. Although for the most part what we'll be using in class is we'll be looking at the force from the magnetic field, and then we can always incorporate additional information on the electric field. In general, and I introduced this in all of the classes, what it actually looks like is this: QV cross B. And we talked a little bit about this cross, that X there. That's a very special type of multiplication. It's vector multiplication, and it ends up with a vector result, as you can see. What we've done is we've simplified it down where we've got an understanding that we use the right-hand rule, which we'll talk about in another video, to actually find the direction, and then we simplify this guy down into the following. We can take the magnitude, so the actual value of that force, without its direction. So we're just taking the scalar value of it. Q, V, B. So we multiply all of them together and then multiply it by sine of the angle between our two vectors, between the velocity and our magnetic field. Now a common angle for us is going to be 90 degrees, just so we can simplify this where it becomes sine of 90. But that may not necessarily always be the case. In general, you can find out which way your V points, your velocity, and which way your magnetic field points, find the angle between those two, and that's what you put in for the sine. So, let's see the actual problem with this one. The one we're going to look at is a particle with a charge of 2 coulombs. 2 coulombs is going to move into a magnetic field, a uniform magnetic field, and it's going to travel perpendicular to that magnetic field. In this case, I'm just going to draw it where they're at a nice right angle. This guy's going to be moving to the right, the magnetic field is going to be pointing up. All the information I give in this problem is that the velocity, the way this guy is moving, is perpendicular to our magnetic field, which means theta is going to be 90 degrees. Makes it a bit simpler on us. I also tell us that the magnetic field has a strength of 0.14 Tesla. Now, as a reminder, that's kind of a large value. It's not an incredibly large value, but it's a decently large value. Remember that the magnetic field of the Earth is something on the order of, let me see if I can get this right, 0.234, I think this is right, Tesla. It's half a Gauss, and Gauss is, well, 1 Tesla is 10 to the 4th Gauss. So it should be this. This is the magnetic field of the Earth. So compare that to this. This is a pretty strong magnetic field, all things considered. This guy is probably going to be, it's pretty comparable to, say, a decent refrigerator magnet, maybe. Something like this guy. And so it sticks to, you can't see it over here, but it sticks to the board pretty well. If we take one of the fancier neodymium magnets, we've got the sphere here in this bag. You can see that it takes some effort to pull this ferromagnetic spring off of it. And I'm going to put it back in there. And, oh no, it's by other magnets. I'm going to keep it away from those. Those neodymium magnets, the rare earth, the shiny ones, they're usually, the low end is probably going to be with these guys, maybe some of the smaller ones, but the more powerful ones are going to get up to the order of 1 Tesla. It's going to be their surface field anyway, so once you get a point-blank range. All right, so those asides done. Let's get back to our problem. We know our charge, we know our magnetic field, and I tell you that it's moving with a velocity of 240 meters per second. Okay, so our equation that we looked at, our Lorentz force, and I just want to know what I asked for is the acceleration. What's the magnitude of the acceleration that this particle feels? So let's start off. We're actually going to find our Lorentz force. Okay, so I know that it's going to be QVB times sine theta. Well, my charge was 2 Coulomb. My velocity was 240 meters per second. My magnetic field was 0.14 Tesla. And sine of, we had 90 degrees between them because I tell you that they are perpendicular. So I multiply all these together, and I end up with, if I've done my math correctly, 67.2 newtons. Now I want to, however, not the force, but the acceleration. I also give you, and I forgot to mention it, I apologize, the mass is equal to 3 kilograms. Whatever this particular object may be, it has a mass of 3 kilograms. So about 6 pounds or so. So it's not a small object. Okay, so I take that. Now I know my force, which is equal to 67.2 newtons. I want to find the acceleration. So I'll probably need an equation where I can relate the force acting on something and the acceleration. And I recently brought up that there was a mass, so hopefully you're immediately thinking of this, Newton's second law, F equals ma. Now we know our force. Our net force is 67.2 newtons. That's going to equal our mass, which is 3 kilograms, times our acceleration. We divide both sides by 3. And we find that in the end, our acceleration for this object is 22.4 meters per second squared. A little over 2 Gs. So, if you keep in mind that it's a 6-pound object, it's not a small amount of force or acceleration.